Let's talk about rational functions. A rational function is a quotient of polynomial functions where you've got a polynomial on the top and a polynomial on the bottom. You need to make sure the denominator function is not a zero function. So the first thing you always want to do is figure out your domain. So you're going to make sure that the denominator does not equal 0. So in this case, 2x would not be negative 3, so x cannot be negative 3 halves. Figuring out the domain is important because that tells us where we'll have vertical asymptotes. So you can also have horizontal asymptotes in a rational function. Here's what you need to check for. You've got vertical asymptotes at the zeros of the denominator, and the graph of the function has one or no horizontal asymptote determined by comparing the degrees of your numerator and your denominator. So you're going to look at the degree of the numerator and compare it to the degree of the denominator. If the numerator is less than the denominator degree, then you've got a horizontal asymptote on the x-axis. If they're equal to each other, then it's equal to the ratio of those lead coefficients. Okay? And if the numerator is greater than the denominator, you have no horizontal asymptote. You have what we call a slant or oblique asymptote. So let's look at some examples. Okay, so here I've got f of x equals 3x squared minus 6x over x squared plus 2x minus 15. And you always want to completely factor everything first. So I'm going to take a 3x out. And I have an x plus 5, x minus 3. Okay, so my vertical asymptotes are going to be at negative 5 and positive 3. And the degree of the numerator is the same as the degree of the denominator, so it's going to be the ratio of the lead coefficients, in this case 3 to 1. So y equals 3 is my horizontal asymptote. Okay, let's check for some x-intercepts. I'm going to set the numerator equal to 0, and I get x-intercepts at 0 and 2. And now, let's do a quick little sign chart. I've got interesting things happening at negative 5, 0, 2, and 3. Asymptotes at negative 5 and 2. Intercepts at, no, I'm sorry. I've got asymptote at negative 5 and 3. And intercepts at 0 and 2. So let's pick a point to the left of negative 5, like negative 6. So if x equals negative 6, then this factor here will be negative. This factor will be negative. This one will be negative. And this one will be negative. So 4 negatives add up to a positive. So any number that is less than negative 5 will give me a y value that is positive. So I'm thinking the graph is doing something like that. Okay, now let's pick a point between negative 5 and 0, like x equals negative 1. Now I'm going to have a negative times a negative over a positive times a negative. 3 negatives make it negative. So I'm thinking the graph is doing something like this. And then let's go ahead and plug 1 in, because that's an easy number to work with. So I'm going to get 3 times negative 1 over 6 times negative 2, which reduces to 1/4. So I've got an actual point at 1, 1/4. So the graph is going like this. And then finally, pick a point that's greater than 3, say 4. And when x equals 4, I've got positive times positive over positive times positive. So 4 positives make it positive. So this graph is doing this. So that's a quick way to sketch a rough graph of a rational function. Okay, this example, we have the degree of the denominator is greater than the degree of the numerator, which means that y equals 0 is our horizontal asymptote. And let's factor. And I have vertical asymptotes at -1 and 1. I have an x-intercept at -2. And let's plug in 0 for y. I'm sorry, 0 for x to get any y-intercepts. And I'm going to get that f of 0 is -2. So I have a y-intercept at -2. Okay, sign chart. -2, -1, and we know it's negative between -1 and 1. So pick a number to the left of -2. And when x equals -3, I've got a negative over a negative times a negative. So this is all negative over here. Okay, so it's doing something probably like this. Which brings up an interesting point. It is possible to cross a horizontal asymptote. You will never cross a vertical, but you can cross a horizontal asymptote. Okay, and then this is going down like that, going down like that. And if we pick a point past 1, say 2, I've got a positive over a positive times a positive. So everything's positive. Now I would probably want to get some more points out here to see what the basic shape is, but in the interest of time, we're going to move on to the next example. Okay, now here it looks like we're going to have a vertical asymptote at x equals 6, doesn't it? But let's factor first. Have the difference of two squares on top, and notice that those factors cancel. And so what that means is I'm going to have a hole at x equals 6, not an asymptote. So I'm just going to graph the line y equals x plus 6. So that's right here. And I've got a hole there. And that's what that rational function looks like. Okay? Oh, wait a minute. That's not right. Let's start over again. At x equals 6, I've got a hole. So at 6 comma 12, I've got a hole. There we go. That's better. And have a y-intercept of 6. Okay. Last example. On this rational function, the degree of the numerator is greater than the degree of the denominator, so we are going to have a slant asymptote. Let's factor. So I'm going to take an x squared out of the first two, leaving me with 2x plus 1. I'm going to take a -4 out of the second two, leaving me with 2x plus 1. And then the denominator is going to factor into x minus 1, x minus 2. And so on top I can take a 2x plus 1 out, leave me with x squared minus 4. Underneath I already got it factored, so I don't do anything, and I can factor one more time on the numerator. So we're going to have a hole at x equal 2. Let's just keep that in mind. And I've got a vertical asymptote at x equals 1. and I have x-intercepts at negative 1/2 and negative 2. And let's see what else we can do here. Let's do a quick sine chart. So if I pick a point to the left of negative 2, say negative 3, then this factor will be negative, and this factor will be negative, and this factor will be negative. So it looks like everything is going to be negative down here. Okay, let's plug in x equals negative 1, and I'm going to get negative 3 times 1 over negative 2. So that's going to have a point at 1.5. So it's probably doing something like this. Okay? And in the interest of time, let's jump over to FluidMath and have it graph it for us. And sure enough, that looks like what we were working with. And if I zoom out, you can see the hole at x equals 2, and then we have a slant asymptote going along here. Now how can we figure out what that slant asymptote is? Well, that's pretty simple actually. We are going to do polynomial long division. Okay, so I'm going to go x squared minus 3x plus 2 into 2x cubed plus x squared minus 8x minus 4. I think that's what it is. Yeah. Okay, so I've got a 2x right here, which gives me 2x cubed minus 6x squared plus 4x. Subtract, I get a 7x squared, and then a negative 12x minus 4, so I have a plus 7. 7x squared minus 21x plus 14, and that's all I care about because the oblique asymptote is the equation of the quotient disregarding what the remainder is. So if I graph f of x equals 2x plus 7, now you can see how that oblique asymptote works.